Hello, this lecture will be about the moon and how it moves in space. Specifically, how it moves relative to Earth and how that affects how we view the moon from Earth. Furthermore, we will use information that we learn to see what other implications it has in the solar system and universe. To begin, we will analyze a graph that displays moon data taken every day at 12 p.m. from September 1st, 2021 to October 1st, 2021. This is 31 days of data. This data represents the position of the moon relative to Earth at 12 p.m. every day. In the center of the graph is a green circle. This is the Earth. On this graph, the Earth is at the origin, which is x equals 0 and y equals 0. In the circle around the Earth, which goes through all four quadrants of the graph, is the moon data. There are 31 dots which represent the moon data on a given day. The blue dot represents the moon on the first day of observations, September 1st. The red dot represents the moon on the day it completes a full orbit on September 29th. This means that the moon has gone all the way around the Earth and is back in the same spot it was when the observations began. Although there's a dot closer to the blue dot, the current red dot was chosen as the dot to represent the moon after a full orbit because the dot, which is closer to the blue dot, has technically not completed a full orbit. So you can see here, I don't know if you, hopefully you can see my mouse, but this black dot is much closer to this blue dot, but there is this little bit of space in there. So that the orbit's not complete. This is the closest dot after the blue dot. The orbital period of the moon takes about 27 days. Something to note is that although I have said it takes 27 days for the moon to complete an orbit, the red dot is the 29th data point recorded. This is because there are more data points than there are days. This is possible due to how the data was recorded. On the first day, a data point is recorded, but a day has not passed. After 2 data points have been recorded, 1 day has passed. Although the data points were taken on 2 separate days, there's only 1 day between. So we can view the effects of this on the graph. As noted before, the red dot is almost what seems to be the distance of an entire elapsed day from the blue dot. See the distance here. This is the full day, but we're almost back here. This means that the orbital period was actually completed closer to the day before. If you round down, then we can see the orbital period was 27 days, and we see where the extra 2 days come from. This is my best educated guess for the difference in numbers. Now let's talk about how all this affects the way we view the moon from Earth. The moon is assigned phases based on what percent illumination the moon is. For example, the moon is referred to with the phase full moon when the moon is close to 100% illuminated, like 99%, let's say, close to 100. On the day of first observations, the moon was in the phase waning crescent. The moon is referred to with this phase when the illumination is below 50% and is decreasing because it is waning and resembles a crescent shape. On the day of the orbital period completion, the phase of the moon was also waning crescent. Although the phase is the same, this is not to say that the moon appeared the same. On September 1st, the moon was 29.8% illuminated. On September 29th, the moon was 46.1% illuminated. This is because the time it takes for the moon to be similarly illuminated as it was the previous cycle is different. It's called the solar month or synodic period, different from the orbital period. This period takes 29 days. This is 2 days longer than the orbital period. The same phenomena takes place within the solar month, where there are 31 data points, 2 more, but for the same reasons, there are 29 days. The difference results from the Earth's motion around the sun. The moon must make a more than complete revolution around the moving Earth to get back to the same phase in respect to the sun. Now, we will discuss what other implications this information has about the natural world. For this, we look to Johannes Kepler. My mistake, Kepler. This is him. He's a German astronomer and a mathematician who made fascinating discoveries in the early 15th century. Kepler discovered 3 laws which concern planetary motion. Kepler's third law is of interest to us when analyzing the moon and what it can tell us about Earth. Kepler's third law states that a planet's orbital period squared is proportional to the semi-major axis of its orbit cubed, or p squared, and this little symbol here means proportional to. I'm not too sure how to do exponents in the slides, so it's just 2 and 3. So p squared is a cubed, or p times p proportional to a times a times a. A semi-major axis is the average distance between 2 astronomical bodies when one of the bodies orbits the other. For the Earth and Sun, this is 1 astronomical unit. The Earth and Sun are 1 astronomical unit apart because the average distance between the Earth and Sun was used as the model for the AU. 1 AU is 150 million kilometers or 90 million miles. AU is the unit used to measure a semi-major axis. The semi-major axis of the moon is 0.00258 AU. The unit for an orbital period in Kepler's third law is Earth years. So the orbital period of the moon is 0.07 Earth years. That's how much 27 days is. It's 0.07 Earth year, 7% of the Earth year. Then, in the late 15th century, Isaac Newton, an Englishman and mathematician, astronomer, this is him, discovered fundamental laws concerning gravity. Newton applied his discoveries to the work of Kepler by introducing mass of the sun and a planet in units of sun mass to Kepler's equation. 1 sun equals 1 sun mass. This looks like a cubed equals m1 plus m2 times orbital period p squared. Including mass allows us to use this formula in a new way. If we can measure the distance or the distances and orbital periods of objects acting under their mutual gravity, then the formula will permit us to deduce their masses. This is because the mass of a planet is minuscule relative to the mass of the sun. So when the 2 values are added together, the sum is very close to 1 sun mass. So in the formula, the factor m1 plus m2 would now be approximately equal to m1, the mass of the star. This, since the planet's mass is so small by comparison, then the formula just becomes semi-major axis cubed equals m1 times orbital period squared. And we can use this to solve for m1. Then we have the mass of m1. The same principle can be used with the moon and the Earth to calculate the mass of the Earth. So back here, we have the orbital period, 0.07 Earth years, and the semi-major axis, 0.00 or 00258 AU. And we would use those numbers in this equation here. And you calculate the mass of the Earth. This principle can be used with any astronomical body in the universe which is being orbited. Newton's reformulation of Kepler's third law is one of the most powerful concepts in astronomy. Our ability to deduce the masses of objects from their motions is key to understanding the nature and evolution of many astronomical bodies. So, in this lecture, we have reviewed and talked about how the moon moves in space, how that affects how we see the moon from Earth, how it moving in space, and we discussed further implications of our data and what else we could find. Thank you.